Okay, so let me continue on the lecture first. Then we will talk about the quiz. Okay. I want to finish discussing the introduction to transaction. Okay, so I believe this is where we stopped last lecture. So we have, I think by now we have a pretty good understanding of transactions. So in transaction, database systems try to ensure the ASCII properties for the transaction in the system. A stands for atomicity, which I explained in last lecture, which is all or nothing, meaning that the statements or the actions within a transaction, they get executed all together, or none of it gets executed. Okay, so that's what we mean by atomicity. C stands for consistency. Quickly recall the definition of consistency. What consistency means is that suppose at a given time your database is in a state where all functional dependencies are satisfied. So suppose this is your database at time t1, and you have a bunch of functional dependencies that are enforced on this database. And at time t1, all of these functional dependencies are true. There's no violation whatsoever with respect to these functional dependencies. And then from, let's say, from t1 to t2, so this is time, I have executed a bunch of transactions. Let's say I have executed 10 transactions against this database. What consistency means is by the end of this executing this transaction at time t2, all these functional dependencies is still true. Meaning that after executing any given transaction, you do not leave database in an inconsistent state, where inconsistency means that at least one of the function dependencies has been violated. Okay? So that's what we mean by consistency. And I stands for isolation, meaning that each transaction appears to be running on its own without the need to worry about other transactions in the system. And D is for durability. Durability really means transactions, the effect of a transaction persists through system crash. If system has crashed during the execution of one or more transactions, if those transactions have committed, then their changes will be permanently reflected in your database. Okay? So that's what we mean by durability. So right now, we are talking about, on this particular slide, we are talking about isolation. And as I mentioned in last lecture, there are different levels of isolation in a database system. The default level is what we call serializable isolation level. What that says is, you may interleave, you being the database management system, DBMS may interleave action from different transactions as long as the end effect of interleaving those actions from different transactions is the same as one of the serial execution of these transactions. Note that the key concept here is one of the serial execution of these transactions. Meaning that if you have, for example, given this example, you have T1, T8, T10, T8, T9, a serial execution of that, let's say, is T1, T10, T8, T9, T2. If you interleaving actions of this transaction lead to a database state, that's the same as executing T1, then T10, then T8, then T9, then T2, then it's okay. Okay? Then you are okay in the serializable isolation level. You follow me? It is also possible that you, after interleaving action from different transactions, the end effect of the database system is like T1, T8, T9, T10, T2. That's also okay. Which might be different from the current order I'm showing here, but that's okay because the requirement is equivalent to one of the serial execution of these transactions. Okay? And you may wonder, well, isn't that will that lead to some uncertain state of the database management system? Meaning that the database management system will be able to interleave these actions from different transactions somehow lead to different end states because it may be equivalent to different serial order of executing these transactions. Well, yes, that's true. However, keep in mind, this is still true. This is the most important thing, which is no matter how you interleave these actions, and no matter whether the equivalent to this serial order of executing this transaction or another serial order of executing these transactions, at the end of the day, consistency must be still true, meaning that all functional dependencies must still be true. Functional dependencies reflect important business logic in your database. Okay, think about people ordering stuff from Amazon.com. It is true that if I let transaction 1 execute before transaction 2 versus transaction 2 execute first before transaction 1, it may lead to different states. However, the functional dependency, for example, is that the total number of ordering must less than or equal to the number of stock available for a particular item. That is still true. That's the important message here, right? Functional dependency is still honored by the consistency requirement. Okay. So another thing is less obvious, but to keep in mind is isolation level in a lot of database management systems. Isolation level is not necessarily set as a system level parameter. Rather, it is set as a per transaction parameter, meaning that different transactions may be running in different isolation level. And they check the isolation condition based on this per transaction view, meaning that from this transaction perspective, as long as after executing my transaction, for all those transactions in the serializable isolation level, if the end effect is as if I'm executing them in sequential order, then I'm okay. Then for all those transactions in the repeatable rate isolation level, I will compare against those repeatable rate transactions and make sure at the end of the day, the effect is equivalent to whatever it says for the repeatable rate isolation level, which we will discuss in the next slide. So in order to talk about repeatable rate, I first need to introduce a concept called dirty rates. So dirty rates defined as you're reading a dirty data item. And dirty data item is an item that's is overwritten by an uncommitted transaction. An uncommitted transaction writes to an item will make that item a dirty data item. Why we call this dirty data item? Because if the transaction has not committed yet and has updated an item, the value of that item, okay, is not in a stable state because that transaction may be aborted, may roll back, so that the current value of the item is not stable. If the transaction chooses to abort, either the transaction wants to abort by itself or system has crashed. Then the value the item has is no longer valid. And this is a dangerous act because other transactions who start reading this value and using this value for their calculation will be forced to abort as well because you are making wrong decision based on a wrong value. Does it make sense? So dirty data item is dangerous to database management system. However, in certain isolation level, they still allow dirty data item to exist. Why? Because you want to increase the level of concurrency so that you can interleave more actions. As you can imagine, if you block any read to a dirty read item, your concurrency level will be decreased. If you allowed concurrent read to dirty data items, in the contrary, your concurrency level will be increased. So I'll give you an example. Let's say the first transaction, the statement, suppose that's a statement from the first transaction, is trying to update the enrollment number, while the second transaction is trying to compute the average enrollment number from all college. Obviously, if you allow these two statements if you allow to interleave these two actions from two transactions respectively, if the first transaction has not committed yet, then that enrollment number you read for Stanford is considered to be a dirty data item because you run the risk of that the first transaction may abort. If the first transaction chooses to abort, then the average value you have computed is no longer valid. Even if all the other enrollment value you have read from all the other colleges are valid, as long as this one value is invalid, then the whole calculation is invalid. So the second calculation has to be forced to abort. The transaction doesn't want to abort, but it's forced to abort if the first one chooses to abort. But however, on the other hand, if the first one chooses to commit, then the second one is okay. Right? You see the difference, right? So if you do allow the second one to read the dirty data item, the second one can move on with its computation much earlier than the case when you do not allow this guy to read dirty data item. Because in the latter case, if you do not allow the second transaction to read a dirty data item, the second transaction has to wait until the first one commits, which may take a few seconds, a few minutes, or a few hours. Okay? That's the reason why in certain isolation levels, we choose to allow a transaction to read dirty data item so that we run the risk of that you might have to be forced to abort, but in most cases you are just okay. You know, if the first transaction choose to commit. So here's another example. It's very okay. So that's just another example of dirty rate. So that being said, we introduced this isolation level called repeatable rate isolation level. So what is the repeatable rate isolation level? Well, repeatable rate says, first of all, a transaction may not perform dirty rate. So it still doesn't allow dirty rate. And secondly, an item read multiple times cannot change value. An item read multiple times by the same transaction, of course. By the same transaction cannot change value. Of course, unless the transaction itself has changed the value of the item, then that's okay. Okay? Then that's okay. But if you haven't changed the value of the item and you try to read this same item multiple times, its value should not change by another transaction, in other words. So you may wonder, isn't this the same as serializable isolation level? Well, it is not. Let's consider this example. This y-axis is the time dimension. Think about this as time. Okay? So I'm interleaving actions from different transactions. Action 1 from transaction 1, action 1 from transaction 2, and action 2 from transaction 1. So that's the order. You do this first, then do this, then come back here. Okay? First of all, let's check if this is in serializable isolation level. Can someone tell me whether this particular execution is in serializable isolation level? Speed up.
Yes, it is, because the another transaction is starting and first is being done, and the another T1 is continuing.
Okay, so before you say yes or no, let me ask you this. When you are going to check whether this is in serializable execution level or not, how do you check it? You check if the end effect is equivalent to one of the serial execution of these transactions. Okay? And you tell me, in this case, what are the possible serial executions of these transactions?
First, execute the query from the second transaction, and then read the data, because the result is being modified.
Okay,
First
so we are saying is first is T2,
then
then T1, okay? Which is executing the update statement from T2, then execute the select statement twice from T1. What is the other possibility? What is another possible serial execution of these transactions? Well, you have no choice, right? T1, T2, right? You only have two transactions. That being said, let's check if this execution I show on the slides is the same to either this or that. Yes or no?
If it was equivalent, then T1 should be returning the same thing for the select queries as, equivalent to one of those that would either be happening like before or after the insert.
Well, the answer is no, right? The order I show on the board is not going to be equal to this. Why? Because if you do this, you insert Bob into the database, and then you read the database twice for people aged between 10 and 30, and Bob happened to be aged at 27. So Bob will be returned for both of the selection statement. So this Bob, this 3 Bob 27 will be returned twice by the two select statements. You follow me? Whereas the order I show on the board, the first time you execute the select statement, this Bob is not going to be returned. The second time you execute this select statement, this Bob, however, will be returned. Clearly, it's not equivalent to this. Because both times Bob will be returned, but here only the second time Bob will be returned. So it's not equivalent to T2 then T1. By the same analysis, it's not equivalent to T1 then T2, because if you do T1 then T2, what happens? In this case, both times Bob should not be returned, because you insert the Bob after the fact that you have read the database. Whereas in this case, first time Bob is not returned, second time Bob is returned. You follow me? Yes or no? Yes, okay? So, one thing we know for sure, this is not in serializable isolation level.
So I'm confused. I thought I understood that multiple reads will always return the same value, right? And so that would be the equivalent of your option 2 over there, right? Because it would be the equivalent of the insert happening after both selects.
Multiple read of the same item will return the same value. That's a tricky part. An item read multiple times cannot change value. However, this Bob record is not read multiple times by this transaction. It's read only once by this transaction. But regardless of that question, let's ignore that question for now. That's an excellent question, by the way. But let's, for the time being, ignore that question. Forget about repeatable rate isolation level. Let's think about just serializable isolation level. This clearly is not in a serializable isolation level. This is not in serializable isolation level, meaning that if your database is in serializable isolation level, this particular execution will be rejected. Database will not execute these two transactions in this order if you are in serializable isolation level. You follow me? This order will be rejected. Database will not interleave the action like this. However, meaning that database will force you to do either T2, T1 or T1, T2. In this case, there's no way you can interleave the actions of these transactions and still in serializable isolation level. If you are in serializable isolation level and these two transactions trying to execute concurrently, the only possible order the database can execute them is either T1 or T2 then, or T2 then T1. There's no way database can interleave any action from these two transactions if you're in serializable isolation level. Do you follow me? However, if you change your database setting to repeatable rate isolation level, then I claim this order will be accepted by your database. Why? That brings up Eric's question, which is, if it's in repeatable rate isolation level, is it the case that an item cannot change value? Well, the requirement is an item read multiple times cannot change value. In this case, this user Bob is only read once, so how do you define a change value? If you read something only once, there's not even a notion of this item has changed value. For all the other items you have read twice, except Bob. Bob you read only once, but for all the other users you have read twice, yes, they didn't change value. They stay the same. And Bob you read only once, so there's not even a notion of this guy change value. Secondly, a critical observation is there's a commit statement here, meaning that the second time when you execute this statement, when you read Bob, it is not a dirty read because the transaction has committed. It is not a dirty read. You follow me? However, if I change this just a little bit, if I remove this commit statement from here, I commit here, do you follow me? Do all of you follow me? So transaction 2 execute this, but do not commit immediately. It does not commit immediately. It choose to commit after this. Is this still a repeatable rate schedule? The answer is no. The answer becomes no, because if you do that, you will have a dirty rate. If you do that, you will have a dirty rate. Because the second time you are reading from the database, you will try to read this value that has not committed yet. Okay, do you follow me? So in practice, you wonder, then what happens? Well, what happens is, if database try to schedule like that, okay, commits here, and you're in repeatable rate, this execution of this statement will be blocked. When you try to execute this, there will be a block operation inserted by database, so that this cannot be executed until this is finished. You follow me? Yes or no?
But would the second transaction be able to read if the commit was not there, if the commit was not issued there, when you're doing again select star from users, would that read the value of what was when we did during the last class? If there are two independent transactions, this transaction unless there is a commit over this transaction might not know Bob has been inserted. So how would there be a dirty read in that case if there is no commit?
No, I don't get your question,
So
but
if there is no commit in the transaction.
if there are no commit statements,
So when there is a selection, the second selection, will the value of Bob be read by this transaction? Will the transaction know Bob?
no, if you have no commit statement here,
Yeah.
this select will not read this value because by repeatable rate isolation level, this schedule as it is become an invalid schedule, meaning that database will not accept this schedule to execute them in this order. That's why I introduced this block concept, meaning that if the database system is given a schedule like this and its database is in repeatable rate isolation level, this will be blocked. If you try to execute like this, this will be blocked, so that I will execute this, then this, and then this. And even as if it is, I put commit here, then in repeatable rate, this is okay. I will allow this to execute, I allow this to execute, then I read this. In repeatable rate, that's okay. But if I change my isolation level to serializable isolation level, then even this schedule is not allowed. You follow me? So if you try to give a schedule like this to the database system and database is in serializable isolation level, this will be rejected. Database will rearrange the execution order so that it's T2, then T1, or T1, then T2, if it's in serializable isolation level. Do you follow me?
When people saying the query 2 is blocked in the repeatable read fashion, so does the timeline, on the basis of timeline, if I consider this query has been cached or something?
Well, what happens is block is a conceptual thing, right? So what really happens is database, when database are given these transactions to execute concurrently, database will come out with a valid schedule. You as user does not have the choice to give database a schedule. Database schedules the transaction themselves. So what really happens is it's not the block is really a conceptual thing for us to understand things better. What really happens is database will not even come up with a schedule like this in the first place if it's in serializable isolation level, and database will not schedule them such that commit is here and insert is here. You follow me? That's the way to view this. You as database user does not have the power to give database a schedule. Tell database, oh, I want to execute these transactions in this fashion. Do this first, do that. No, you do not have that power to do that for DBMS.
It seems like it'd be hard for the database to do that schedule because it has to know that Bob would appear in that query, just based on the values that are being inserted.
Excellent question. That's something we're going to discuss right next, which is called concurrency control scheduling in database management system. And the scheduler I'm going to introduce assume no prior knowledge about the workload the database system going to receive, meaning that it's a dynamic scheduler that go on the fly. However, recent research have shown that if you assume you know the workloads you're going to have, meaning that you know what type of transaction you're going to have ahead of time, then you can do a static approach that's much more efficient than the dynamic ad hoc approach. However, you have to know the workload ahead of time, which is quite intuitive. If you know what you have to schedule with, you can do a better job. If you don't know what's coming, you schedule on the fly, you're going to be more expensive. Meaning that less concurrency in the execution of your transactions. We will talk about that in the coming slides. Okay? All right.
I've got one more question.
Yeah, go ahead.
So it's not the fact that you've got interleaving that makes it not serializable. Like you could have two transactions
Totally.
that are interleaved and that are somehow equivalent to it.
Totally. You can have the mere fact that there are interleaving actions, that's not the cause of the problem. You can totally interleave actions from different transactions and still be serializable. I'll give you a simple example. So let me give you an example where it is serializable and we're interleaving action from different transactions. Okay? So let me read the value A here. A is a record, right? Whatever. And B, T2 says, so I update the value of B. Yeah, okay? I update the value of B. Then I read the value of A. Yeah, okay? Then I also write the value of A. And then here I'm gonna let's see whether I can do this right. Yeah, I read the value. So I can write the value of C here. I write another value C. Okay. Then I update value C. So here I commit. Here I commit. Okay, something like that. Okay? So I am interleaving action from two transactions. And you can show that this is the equivalent to T2 then T1. Clearly it's equivalent to T2 then T1. Why? It's like I execute all this first, then I execute all of this first. After that, I'm still, in this case, I'm reading the value of C written by T2, and here I'm still doing that. In this execution, at the end of the day, T1 determines the final value of C, and T2 determines the final value of B. So that's still the case here. You follow me? However, this is not the same as, it's not equivalent to T1 and T2. Right? Why? Because if you execute T1 first, it's not equivalent to this because T1 is reading a value of C that's not determined by T2. Is that okay? So this is a serializable schedule because serializable acceleration level says you only need to be equivalent to one of the serial executions. You don't have to be equal to all of them because that's basically impossible.
So even though serializable levels are typically stricter than repeatable reads, we still have a dirty read in a serializable.
Well, that's an excellent point. Okay, in this case, we do have a dirty read. We do have dirty read. Do you see that? So that bring up a really tricky question, which is, does serializable acceleration level allow dirty read? Well, the answer is here the answer. Okay. In my discussion here, I assume both transactions do commit in the end. So whether you have dirty read or not doesn't really matter because I know they're gonna commit. In an online system, or in OLTP system, online transaction processing systems, you don't know whether a transaction will commit in the end or not. You don't know that. Either the transaction may abort by the user or system may crash. For example, system may crash right here. Or system does not crash, but after you read this, I decide to abort. I do not want to commit, I abort. Then in that case, this is no longer equivalent to a serial execution of these transactions. So the answer to your question is in OLTP, in online transaction processing, serializable isolation level does not allow dirty read. Even if the end effect is equivalent to a serial execution, but in online system, we just don't know that. We just don't know whether they will commit or not. In this example, I'm using this as an argument to show you the effect that what's the difference between serializable isolation level and repeatable rate isolation level. And I know they're going to commit. In that case, this is a valid schedule. But in an online TP, OLTP system, if you are in serializable isolation level, this will not be allowed because of the dirty rate. You may wonder, how does the system figure this out? And that's essentially back to Charlie's question earlier, which is the scheduler algorithm, which we're going to talk about in the coming slides. Okay? So the difference between serializable and the repeatable rate isolation. And by the way, most commercial database systems have four different isolation levels. The strictest isolation level is serializable isolation level. By strict, I mean less concurrency, less interleaving of action from different transactions. Serializable isolation level at the bottom. Repeatable rate is the next level on top. When you go up like this, you increase the concurrency of your system, meaning more interleaving of action from different transactions. However, more chance of abort and dirty rate and all that stuff. In other words, less consistency in the way you're executing these transactions. Okay? In this class, I will only cover serializable and repeatable rate because these two are the most popular isolation levels. By default, most database systems out there, I think almost 100% of them, are either, by default, are either in serializable isolation level or repeatable rate isolation level. The other two isolation level on top, going beyond repeatable rate isolation level, they do have more concurrency allowed. However, they lead to more abort, they lead to more inconsistency rate and things like that. So they're less common in practice. People only use them in certain conditions where they know what kind of workload they have, so that using that particular isolation level will increase the concurrency and without introducing all these problems. Because I know what my workload is going to look like, and my workload will not lead to those weird behaviors in those isolation levels. Then I'm going to use those isolation levels to just increase my my concurrency. Question?
So what you're trying to say is in online transaction processing systems, if they're serializable, then transactions are locked basically till in one.
No. So yes, in online system, what happens is every transaction must go through the same concurrency control scheduler, and the scheduler will choose to block, not at the transaction level, but at the action level. They will not block the entire transaction. They will block certain action of a transaction.
Okay, so it actually does try to figure out if actions can be interleaved or not.
In an online fashion. That's basically back to my question to Charlie earlier. If you know all the workload ahead of time, you can do static scheduling, which typically is going to be much more efficient than online scheduling because you know everything ahead of time. But if you're in OLTP, meaning that transaction can't dynamically come and go in an online fashion, you cannot predict what kind of transaction you're going to have or what kind of actions this transaction is going to do. Then you want to schedule them in an online fashion. In that case, yes, action from a transaction may be blocked. So the difference between so now we understand the difference between repeatable rate and serializable isolation level. And the major difference is really, later on we're going to introduce the concept of lock. And the major difference between the two is that in repeatable rate isolation level, there is no range lock. There is no range lock. In the earlier example you have seen, a range lock is to log the range between age 10 and 30. So that while one transaction is making a rate over this range and that transaction has not committed yet, I will log this range, not only the records that are currently in the database from this range, but log the entire range, so that the insertion of Bob, age 27, will be rejected, will be blocked.
So
Is it possible if we allow things to be interleaved that within a transaction you could see an inconsistent state of the tables?
No, within a so the SC property, which I just read, the C is consistency, holds for all transactions, no matter how many transactions you have, meaning that it holds for the special case that you only have one transaction. In other words, even if you have a single transaction, you still need to honor all the function dependencies you have currently in the system.
So the scheduler doesn't have to.
Well, if you are in one transaction, there's no notion of dirty read, by the way. For the transaction itself, it's okay to read an item you have updated, even if you have not committed yet. Dirty read is a definition across multiple transactions, not for one single transaction. Okay?
But could you read the reasons? Okay, no.
Well,
I guess-
the whole point of dirty read is to get rid of what we call cascading abort, meaning that abort of one transaction will lead to the forced abortion of the other transactions. If you only have one transaction, this is not a problem to begin with, right? Because if you want to abort, you abort. As long as it's kind of like in this, if you think about human society, you can decide whatever you want to do on your own body. As long as you are not affecting others, I don't care. But if your action leads to an undesirable state for another person, that's where it becomes problematic. So a single transaction, you do whatever, I don't really care. Because that's your own thing, right? That makes sense?
Yeah, and I guess the dirty reads, preventing dirty reads would make sure that you see a consistent
Yes.
view of.
All right, cool. So database system love to have read-only transactions because read-only transactions get rid of all these problems. First of all, one observation is clear. If you know you're going to have read-only transactions, you can interleave actions in any order you like. It doesn't really matter. It will be in serializable isolation level, it will be in repeatable read. In any isolation level, if you have read-only transaction, you can interleave any way you like, independent of isolation levels. For example, these are read-only statements, right? Because you are not updating the database variable. So, to give you a quick summary, which is essentially what I have said. The default typically is either serializable, the slide need to be updated a little bit. The default is usually always serializable, but increasingly I see a lot of default level at repeatable rate. I see a lot of default at repeatable rate. So the default is either serializable or repeatable rate. If you go up in the stack, meaning that if you go to a weaker isolation level, you have more concurrency, but you have weaker consistency guarantees. If you go down the stack, you have stronger consistency guarantees, but you have weaker, less concurrency allowed in the system. Okay, so that's so much about isolation. That's so much about isolation. ACID. We're done with the I, and we will come back and visit this, talking about the scheduler. That's kind of related to Charlie's question. Now, what about durability? What happens if system fails? Well, each transaction's changes are reflected either entirely or not at all. This brings up this concept called atomicity and durability. Atomicity means that the actions in your transaction are either fully reflecting a database or not reflected at all. What do I mean by that? Well, if you look at this example, if transaction 2 has committed, then both of this change must be reflected in the database, meaning that the value B, the write of B and write of C must be reflected in the database. You cannot have a state where T2 has committed and B is being written by T2 but C is not. You follow me? So that's all or nothing. All or nothing. On the other hand, if T2 tries to abort, you cannot simply restore the old value of C and while not restoring the O value of B. Or restoring the O value of B but not restoring O value of C. You have to restore the O value for both of them. Or nothing, or nothing. Durability. Durability says if a transaction has committed, after this point, I don't care what your system has done, whether your system has crashed or whatever, these changes must be permanently reflected in your database. You may wonder, isn't that trivial? By the time I have committed and I have updated some value, these changes should be reflected on this already, right? And this is permanent. This is non-volatile. Well, keep in mind, update happened at the buffer level, not at the disk level. By the time you have committed, it merely means that these two update operations has caused these two pages holding the value of B and C to be dirty in your buffer. If system has crashed before those dirty pages from buffer has been pushed to the disk, it's like this has never happened before, which is wrong by the durability requirement. Because once I have committed, I don't care what you do. You need to make sure my changes are reflected permanently in your database. Okay? So let's give you, yeah.
I want to ask that is that possible that the system crashes when we write in the disk?
It's possible, yeah.
So that means we will lose some data.
We will.
We will lose some data.
Well, we will talk about how database management system ensured even that happened, it can still recover. Okay. So let me kind of pause for just a little bit. This last part of the course, okay? We have gone through a lot, right? We talk about SQL, relational algebra, and all that. If you think about what we have covered before the midterm, compared to what we're talking about now, in my opinion, relational algebra, SQL, those are trivial stuff, easy stuff. Core optimization, core execution, those are a little bit more difficult than relational algebra stuff. But compared to what I'm going to discuss in the next two lectures, they're easy. Okay? So I do ask for your attention for what's coming next. The concurrency control and crash recovery, these are not easy subject to understand. Okay? This, in my opinion, is the hardest part of the course. Hardest part of the course. The crash recovery, in particular, in my understanding, my view, it is harder than implementing the B+ string. Of course, I'm not asking you to implement this, but just to understand the concept of it, how it works, is harder than that B+ string implementation project. Okay? And this, unfortunately, is on your final test. Okay? So I do hope you are impressed. Okay, isolation is achieved by logging, which I'm going to talk about in a minute, the concurrency control schedule. What about durability? Back to Yen's question. Durability is achieved by logging, which again I will talk about in details in the coming slides. But just remember, isolation is achieved by logging, durability is achieved by logging. What about atomicity? Well, atomicity is also achieved by logging, because by logging the actions you have done, I can either redo or undo. Undo is to ensure none has happened. Redo is to ensure everything must have happened. Okay. And abort, I think we talked about abort already, right? The abort, the important thing to keep in mind for abort is all or nothing for atomicity. If a transaction chooses to abort or is forced to abort by system crash before the transaction has committed, you want to make sure all the changes made by this transaction is erased from the database. Consistency, we talked about this, right? So an important fact you need to remember is serializability automatically gives you consistency. Why? Because if you are in serializable isolation level, no matter how you interleave these actions, at the end of the day, the effect is the same as a serial execution of these transactions. And as I argued earlier, each transaction in its own ensure that database is consistent. So that if you execute them in serial order, obviously database is always in consistent state. So serializable isolation level automatically give you consistency. Because in essence, you are executing the transaction in sequential order, and each transaction in its own must order all function dependency. And if you execute them in serial order, the database still honor all function dependencies. That's just a simple argument. Okay, so that's the SC property, and we're done with the overview of transactions. Now, let me talk about quiz. Unfortunately, I'm not able to allocate. The quiz number 3 cover a lot of content, right? So I'm not able to, I give 40 minutes for quiz number 3. And I just don't have the luxury to give you guys 40 minutes to do it, given the things I want to cover. So what I will do is I have released quiz number 3 on the course homepage under the homework solution area. And it takes 40 minutes to do, of course, without the solution part. So you will do this quiz number 3 between now and Thursday lecture on your own, using 40 minutes of your time. Closed book. Keep in mind, quiz is a closed book. And at the beginning of Thursday lecture, I will use 10 minutes to go over the solution. So you choose, if you choose not to do it, of course, it's not my business, right? If you choose not to do it, that's fine. But in my opinion, you are losing out because you lose a valuable opportunity to test yourself. So quiz number 3 is out, 40 minutes, do it. Closed book. And on Thursday lecture, at the beginning of the Thursday lecture, I will use 10 minutes to cover the solution. Yeah, go.
Is it an open calculator?
Yes, you can use calculator. Yes. Open calculator, but not open book. Final exam, however, is open book, right? I just want to create a little bit more pressure to you while you're doing the quiz, so that if you're used to the quiz, you will definitely be comfortable in the final exam because it's open book. If you can live with $100, you can obviously live with $150, right? Oh. All right, so now let's move on to the next lecture. Okay. So that's the semaphore. So I use semaphore because it bears some similarity to semaphore in the signal to control the channels. This is just an overview of transaction I can skip. And concurrency in DBMS. Well, the point is, keep in mind, we're talking about, like I said, I'm talking about, for now, for the purpose of this lecture, of this class, we focus on OLTP, meaning that it's an online transaction processing system, meaning that we do not assume workload is known ahead of time. We are given transaction in a dynamic online fashion. Transaction may come and go at any given point in time. I want to have a concurrency control scheduler that ensure a particular isolation level. In particular, we focus on serializable isolation level. We focus on serializable isolation level. Okay? Okay. And database achieves concurrency by interleaving action from different transactions. And each transaction must leave database in a consistent state, meaning that each transaction must honor all functional dependencies in your database system. And because of that, like I said earlier, if you have that and you are in serializable isolation level, automatically, no matter how you interleave these actions, your database will always be in consistent state, meaning all functional dependencies will be ordered at all times, because at the end of the day, serializable isolation level tells you the interleaving of these actions is equivalent to one of the serial execution of those transactions. And if each transaction ensures functional dependencies, the serial execution of this transaction will automatically ensure all functional dependencies. So database always is left in a consistent state. But beyond that, database doesn't really understand the semantics of your transaction. What do I mean by semantic of your transaction? Meaning that in database view, database only see, okay, you try to read this value, you try to update this value. That's the only two type of operation database see for the database object, for table, for item, and things like that. Database doesn't really understand what's the point of you reading this value? What's the point of you writing this value from 100 to 150? What does it mean? What does it mean by changing this value from 200 to 2 million? I don't really care. All I know is you are trying to update the value of this object. The specific semantics, database does not understand and database doesn't care. You follow me? Whether you try to change this to 200 or 2 million, database view that as a write to this object. What's the meaning of it? I don't understand, I don't care. Okay? And the challenge is how do you interleave these actions in a way that you can still ensure serializability.
We're talking about concurrency, are we just talking about interleaving pieces of the transaction? Or are we also talking about kind of like multi-core processor level?
No, multi-core is also no problem. We're talking about interleaving action from different transactions. You can think about this as a single thread. Of course, in modern database management systems, you have multiple cores available. However, that's at the CPU and the memory level. You are trying to executing this action. But from the database point of view, at the end of the day, when you talk about read and write, no matter how many cores you have, you still have one order of accessing the data object. Does that make sense to you? Okay. So this is really a orthogonal question. And this slide talks about atonicity of transaction, which we have just gone over, so I'm going to skip that. And this is a review of ACID properties. Now, let me get on to a real example for you. Okay? So it's a simple example from a banking database. Banking database. By the way, database and the word transaction, they all originate from banking business, because in the early days, the highest demand for database is from the banking industry. From the banking industry. That's why when we introduce transaction, we always use banking examples. Okay? In this example, very simple. I have two accounts with the bank. Let's say I have two accounts with Wells Fargo. Bank account A and bank account B. All I'm doing is very simple. I'm transferring $100 from bank account B to bank account A. So I deduct $100 from B, add $100 to A. You guys do that probably not all the time, but maybe once a month or once a year, hopefully at least. Maybe you have grad student or student only have one account. Maybe that doesn't apply. But I have two accounts, I can tell you. I have maybe 3 accounts, okay? So I do this, okay? And let's say one day I'm doing this. All the other time I'm doing this is fine, I do this all the time. But there's one day, this one day, while I'm doing this, federal government, the Fed met 10 minutes ago, said, oh, we're gonna raise the interest rate for United States, which is currently at 0. But let's say Fed is doing some, I'm a saver, right? So I will be happy if they raise interest rate. For people spend a lot of money, they don't like raising interest rate. But I save a lot of money, so I like to see the interest rate go up. And let's say the Fed met and said, let's raise interest rate. And let's not only raise interest rate, let's raise the interest rate a lot by 6%. And give one time, and give all current bank accounts one-time bonus 6%. Okay? One-time bonus 6%. So that's why you see the second transaction coming in, which is for all you bank accounts, you got 6% bonus. You see that? And this happened to be happening at the same time, So what's the problem? This is like a very simple scenario, What's the problem? Okay, let's look at this. What is the problem? Okay, so if you execute them in serial order, meaning that you do not have any concurrency in your system, you only allow serial execution of transactions, and this is the easy problem, right? Either if there's only 2 choices you have, is T1 then T2, or, you follow me? And in this particular case, the AND effect is the same. You follow me? If you do T1 and T2, what happens? Well, I have 2 accounts A and B. Let's say they both have $1,000 to begin with. Okay? If I do T1 and T2, what's the end effect? After T1, this becomes what? After T2, what happens? Well, times 0.6, 1.06 to both of them. Is that right? Yes or no? What about this? Well, initially it's like that. And after T2? And after T1? Oh, sorry. Is that right? Yes or no? Okay? So that's the effect. But the point is, the total is the same at the end of the day. Because the $100 get credited with 6% interest rate, no matter whether the $100 is in bank account A or bank account B. You can do the math, but intuition is that. The $100 either get credited with 6% interest rate in account A or account B. So in this particular case, a serial execution of them is give you the same end effect. Let's try to interleave these actions. Okay, let's say I'm trying to build a more efficient database. I don't want to do this in this order. I want to interleave actions. So then depending on who you ask, you may interleave actions in very different subtle ways. If you ask me, what I would do it, if I'm the bank account owner, I'm not the bank, I'm the bank account owner, what would I do? If you tell me to interleave these actions, what I do? Well, I will do the following. So this is time. What I will do is, okay, what I will do is do this first. And do this second. And do this next. And what? Okay. Do this last. What's the problem? What's the problem? The problem is the $100 get credit twice. The $100 get the interest twice. You may wonder, what's the big deal? $100, 6%. You got $6 more. I gave you $6. Okay, all right. Let's say I'm Bill Gates now. So Bill Gates definitely transfer money, but I don't think he bothered to transfer $100. I mean, the time it takes for him to click button to transfer $100, he probably make way more than $100 than transferring the $100. Right? So he probably will transfer something like this. That's probably in his ballpark. Right? You know, now you see the incentive of doing it, right? Even for a guy as rich as Bill Gates, I guarantee you, if you tell him you do this, you got 6% interest, free interest, additional on your money, he will do it. Even for a guy as rich as Bill Gates. That's just the nature of human being. Okay? Any one of you, if you have that much money, and I tell you you can get 6% interest for free, who will say no? Raise your hand. Who will say no? I will not say no, I tell you that. I will be honest. But if you tell me it's $100, I will pretend to be nice. That's not the right thing to do. But if it's $1 billion, tell me how to do it. That's just human nature, right? Just human nature. Now, if it's bad to do this, what will bank do? Okay. The bank, of course, will not do this because somebody needs to pay that 6%. Right? bank, of course, is not going to do this. And what are you going to do? Well, bank will do the following. Do this first. I think I might run out of space, but let's try. The bank will do this. Let me see. No, bank will. Yes, bank will do this. What happens? Well, by doing this, bank, when you come to the bank will say, what's wrong? I give you 6% on both A and B. But from your point of view, you're losing out because you $100 doesn't get interest at all. Once again, you probably don't care. $100, 6% interest, $6. But imagine if you're transferring this much money, and bank is giving 6% interest rate and doesn't give you 6% on the 10 to the power 9, will you be happy about that? And who is happy with that? Raise your hand. Let me know. If you do raise your hand, I haven't had my lunch. I'm treating you lunch. You don't even care 6% of 10 to the power 9. Why you care about lunch for $20? Right? So bank will do this. Bank user will do this. In reality, you cannot do either of this, right? Because why? Because we are computer science. We only respect technology. We do not respect what the bank says and what the bank user says, right? So we cannot do either of this. So this is not okay. This is not okay. So the interesting question then is, what is the right thing to do here? Isn't the case that you can only do this or this in this particular case? Meaning that you should not try to interleave action from this at all. Well, the answer is still no, because what you can do is, you can do this. In this case, you can move B here. Then everything is all right. Do you follow me? And this is equivalent to this is equivalent to T1 then T2. And you are interleaving actions. Potentially, you increase the efficiency and throughput of your system. You follow me? Yes or no? But the question is, the real challenge, now comes the real challenge, which is how a database management system can figure out this automatically. We as humans, now after I explain to you what is serializable isolation level, what is repeatable rate isolation level, I give you two transactions like that, you are able to figure this out. But how does DBMS figure out this automatically? And even if I ask you to do this, for two transactions, you feel pretty confident you can do this, right? What about I give you 1 million transactions? Because for a bank, they don't have just two transactions. Right? I don't know how much transaction Wells Fargo has. But think about those investment bank, like trading on stocks. What's the company in Salt Lake City downtown that does this? Goldman Sachs, right? What about these guys? How many transactions they have? I don't know, in the order of probably not necessarily millions, but hundreds of thousands per second, something like that. Right? And if I ask one of you to do this manually, first of all, you may not get it right. And assuming you are very competent, you get it right, by the time you figure it out, stock price has changed. I don't know how much already. Forget about it. Right? They're not going to use you to do it. So somehow we need to figure out an algorithm to do this automatically. And that's something I'm going to discuss in this. So these are some examples. Now, as I argued earlier, database management system doesn't care about the semantics of your transaction, meaning that whether this 100 is $100 or this 100 is just some number nobody cares. I don't care. Whether it's 100 or 10 to the power 9, database system doesn't care. Whether it's 6% interest or 60% interest, I don't care. From database point of view, I only see two things. One is you read the value A, then you write the value A. Read A, write A. You read the value A, you write the value A. You read the value B, you write the value B. You read the value B, you write the value B. You follow me? So that's the view of database management system. And this is critical because this dramatically simplifies the problem we are dealing with. We no longer need to worry about, oh, it's a bank, it's like $100, it's 6% interest. We don't care about all of this. We only care about read and write on some items, abstract as A, B, C, D, or whatever, right? Some symbol to represent the item you have in the database. And the job for a database management system is to figure out whether a given schedule is valid or not. And if it's an invalid schedule, figure out a valid schedule to try to interleave action from different transactions. That's all. That's the database job. Right? That's the database job. And before I talk about that, how to do that, let's introduce a few concepts. First of all, I'm going to introduce this concept called serial schedule. Serial schedule is very simple. Serial schedule is a schedule that executes transactions in sequence, sequentially. So T1, T2, or T2, T1, those are two serial schedules. So this is a serial schedule. This is another serial schedule. You follow me? Yes or no? And then we introduce equivalent schedules. Equivalent. Note that this is the plural. That's singular. So serial schedule is talking about a single schedule. Equivalent schedules are talking about at least two schedules. When you are given two schedules, S1 and S2, they are equivalent schedules if and only if the end effect is the same for the two schedules you have. For example, this schedule right here and this schedule here, they are equivalent schedules because the end effect is exactly the same. So that's what we call equivalent schedules. With these two being understood, next we try to understand serializable schedule. Serializable schedule is nothing else but a schedule that is not a serial schedule by itself, however, is equivalent to a serial schedule. Then that's what we call a serializable schedule. Do you follow me? So by our definition, this is a serializable schedule. However, if you move this to here, this is not a serializable schedule. Why? Because if you check this schedule against this, they are not equivalent. And if you check this against this, they are also not equivalent. And that's the only two serial schedule you have. So the conclusion is this schedule is not equivalent to any of your serial schedules, so it cannot be a serializable schedule. You got it? Okay. Next, we talk about anomalies with interleaved execution of transactions. This part sounds really hard. How can you figure out how to interleave this with so many transactions? But in reality, it's actually surprisingly simple. Because there are only three types of anomalies you need to deal with. Three anomalies you need to deal with. The first anomaly is what we call WR conflicts. By the way, when I say anomalies or conflicts, they always refer to actions from different transactions. For actions in the same transaction, there is no conflict whatsoever. There is no anomaly because that's the order you want to do that. You want to read this first and then write. There's no conflict whatsoever. So whenever we talk about anomaly or conflicts, they refer to actions from different transactions. So the first anomaly or conflict is what we call WR conflict. WR conflict actually captures exactly the thing we talked about earlier today, which is dirty read. Because these are actions from two different transactions. By the way, on the same object. That's another thing. Of course, on the same object. If you write B and then read A, there's no conflict to begin with. So this means write an object A and read an object A, or write an object B, read an object B, by two different transactions. And that creates a conflict. In this particular case, a WR conflict essentially is what? Is a dirty read you're trying to perform. Oh, the other thing I want to emphasize is a pair of actions form a conflict only if the transaction has not committed. If a transaction has committed, then there are no conflicts to worry about. Now, if this W writes an object by the first transaction, and then the first transaction has committed before the read on the same object by the second transaction, there are no conflicts. Don't worry about it, because it's already committed. But if the first transaction has not committed yet, has written an object A, and then later the second transaction tries to read the same object A, while the first transaction has not committed yet, that forms a WR conflict, which is essentially the dirty read phenomenon we talked about earlier. Okay, so give you an example here. This is a WR conflict. Okay, and I think that's about it. Yeah, that's the only WR conflict in this particular schedule. In this particular schedule, this is the WR conflict. Okay? Because the first transaction read the object A, then later the second transaction tried to read it, while the first one has not committed yet. That's a dirty read. That's a WR conflict. You also have RW conflict. RW conflict. Read object A and write object A. And why, you may wonder why we care about RW conflict. Because that basically links to repeatable read. If you read something and you haven't committed yet, and somebody else updates that value, you have the potential to read again, right? And if that happens, you're not going to satisfy repeatable read. Because the two times you read this value A, they have different values. You follow me? Of course, you may argue, who tells you I'm going to read this again? I read this once, you write, I'm not going to read this again, I'm going to commit. Then that's totally okay. But the point is, in an online system, I don't know. I don't know whether you're going to read this or not. I have to prepare for the worst case, which is you may read this item again. Then I need to prevent this if I'm on serializable isolation level. I don't allow repeatable read to happen. Oh, I need to ensure repeatable read. Do you follow me? That's why RW is considered as an anomaly or conflict. Do you follow me? Yes or no? The last conflict is WW conflict, write and write conflict. So this actually, in most cases, is not a big deal. However, in serializable isolation level, we do not allow WW conflicts for the following reason. To give you a simple example, I write the value A, then transaction 2 write the value A. Transaction 2 write the value B, then transaction 1 write the value B. Okay, this example shows you exactly why we do not allow WW conflicts in serializable isolation level. Why? Because if you allow WW conflict to exist, what's going on here? This particular schedule is not going to be equivalent to any of your serial schedules. What are the two possible serial schedules here? T1 then T2 or T2 then T1? If you do T1 then T2, what happens? Well, T2 determines the final value of both A and B. If you do T2 then T1, what happens? T1 determines both values of A and B. Do you follow me? But if you do schedule like this, what happens? While T1 determines value B and T2 determines the value A. This is not good, right? In a lot of real systems, this is not okay. You either let this person to decide on everything or the other person to decide on everything. You don't want to leave the system in a state where somebody determines this, somebody else determines that. So in serializable schedule, we do not allow this to happen. That's why, for that reason, we need to identify WW as a conflict. So in serializable isolation level, we have 3 potential conflicts we need to watch out for: RW, WR, and WW. As long as you prevent any of these conflicts from happening, then you're good. You follow me? That's why we introduce these conflicts, right? Because as long as you identify them and you prevent them from happening, you will end up with a schedule that's serializable. Right? If you have a schedule that does not have any of these conflicts, you guarantee to have a serializable schedule. Do you follow me? So the only thing left is how we can prevent conflicts, any type of conflict like this, like one of the 3, from happening. For that, we use locking. In particular, we use something called strict two-phase locking, or in short, TPR. Two-phase locking. Two-phase locking. And I will talk about that on Thursday.